Hello everybody, how y'all doing? Today we are going to be talking about Gauss's law in specific, and Gauss's law is about electric flux. Now we've been learning all sort of things recently, and they were mostly about some charge, some charge, or some object that is either linear, 3D, or 2D, 1D, or 3D, and let's make these positive actually. Alright, so imagine the whole thing is positive. And we obviously understood or we studied how we can find a point of electric field at this specific point right here. Which, we said that it would go this way. And we also said that this point of charge will make E go this way. Right? At this specific point. But when you look at it as a whole, then the electric field is always going that way. Right? Now, if this was 3D at the tip, well, keep going that way, right? And now when it comes to a single electron or proton, and when we're trying to find the charge or electric field of it, it's always away from it somewhere, right? And that was always what we thought of as the electric field. But what is the electric field actually, and how does it correlate to the strength of the electric field? Now, obviously from our equations, we know E, that's an ugly looking E, E equals the F, the force it causes on a single point of charge. Or obviously there was also E equals to K, Q, all over R squared. And what this told you is that you choose some point away from the charge, and I'll tell you the electric field there, given that you tell it the distance and you tell it the charge. And so since this equation also holds true, then, well, the electric field causes some type of force. But obviously, if you put a magnet in your hand, you don't feel any type of force. It's not the force that you usually talk about where you're like pushing or you're pulling. The electric force is something that only applies on, electric things or electrons and protons. Charged things, really. So when you have your hand and you put a magnet there, you don't feel anything. But if you put another magnet, then you feel a lot of things. And so, what is then electric field? Well, electric field is actually directly correlated to how strong some charge is. And so now if we look at this simulation right here, if I get rid of this, you see this is, let's make it neutral. There's no electric field anywhere. But if I give it just one charge, you can see these electric field lines start appearing. And there's only 4 of them. And as the magnitude increases, the amount of lines increase. Okay, so it's directly correlated. So now, if they are directly correlated, can I say, if I draw a circle right around this, right here, and you tell me how many electric field lines there are, then can I tell you how many charges there are inside? Because remember we said they're directly correlated. So if they're 1, you can tell me there's 8 electric field lines, and I'll tell you there are 3 charges inside then. Well, yes, and that's what Gauss's law actually says. And you pay attention here, if I draw a circle here, the amount of lines that are coming out of this circle are the same amount of lines as if I drew a circle here. And I'll actually demonstrate that here. So, if I have some type of electron, right? Actually, I'll make it small. I don't know why I made it so big. And I drew the electric field out of it. So, it would look something like this. Bear with me right here. This is important for your learning. But, okay, anyways. So, these are our electric field lines going away from the proton. Right? Now, if I take a circle and I draw it around here, as you can see, 1, 2, 3, 4, 5 lines are coming out of there. And if I take a circle and I draw out here, that still holds true. And so what Gauss's law actually says is that, if you give me an area and you give me how many flux lines there are outside, and pay attention, I said flux lines, then I can tell you what the charge is inside. And that is what we call flux, right? So flux actually is what we call these bunch of lines. And so you see this, if I take a towel and I cover this thing in a towel, then there's these flux line going through the towel, right? And so you can see if I, well, get a row of dipole and I get rid of all these ones. Actually, I'm gonna get rid of these ones. You see these flux lines. If I see these flux, I said flux lines. Okay, you see these flux lines or electric field lines. If I take a paper and I put it here, then these lines are still going through. And we know that's true is because if you have a magnet and you put a paper in the middle and you know, a magnet on the other side, they'll still attract. And you'll feel the same thing even if you do with a table, considering that the magnet is strong enough. And so this is what flux lines are. And now to calculate these flux lines, we have an equation that states the following. If I take the electric field that there is at some point, so let's say, actually, new page. Okay, so if I have a electron or a proton, and this will obviously cause an electric field this way. If you tell me what the electric field there is here, and you tell me the area you're covering it by, then I can tell you the charge that's in there. And so the equation, if I can fix this and make it look pretty. So the equation says the integral, and why is this the integral? Is because obviously we gotta sum all these electric field lines because there's multiple of them. It's not just one. And also because what if I make an ugly looking surface? What if I go and create a surface like this? And you still tell me the same? Well, pay attention to this. If this was my electron and I have all these lines out, the electric field lines will be the same if I made a perfect circle, or if I made, oh, that was actually a horrible circle, or if I made like a long circle like this. These lines will still be the same. And so, as we can see, it doesn't depend on the shape of the object either. So, that's why we integrate, is because we have to account for these weird looking pieces. If we don't, then how are we going to integrate this? We can't just make it a perfect square. Because in some cases, what if there was an electron right outside here? But I didn't want to account for it, so I had to, bend over. Well, bend around, I meant. Bend over. Okay. Anyways, so, the integral here, by the way, ride lessons today. Sorry, guys, but I had to stay up somehow. Anyways, so the integral is, so what I was saying, that's why we take the integral. I hope you're not confused. Anyways, so it's the electric, so you give me the electric field at some point, and you give me the area of what you're trying to get the flux through, and now I will tell you the charge inside this area that you just made, divided by epsilon. Oh, this is epsilon naught. It's just a constant, some free space constant. But you can think about it is that if you give me an electric field line, or the electric field strength, sorry, because you know how we said the strength depends on, so the charge depends on how many electric lines it makes, or flux lines. And so this is actually the flux. And so flux states is the flux, this is the flux symbol, caused by this electric field, is equals to the E times the A. So you give me the electric field line, and you give me the area, and I'll tell you how many arrows there are. That's what this represents. Remember how we said in our simulation, we said, let me use just one. Actually, oops. Yeah, you know what? We'll just use one. And I'll explain more to it. So, what it's saying is, if you give me this circle, and you tell me, the electric field that is inside, and you give me the area, then I can tell you how many arrows are coming outside. And that's what the flux is. It's these lines, all right? And so obviously these lines, like we said, they go through objects, and that's really all Gauss's law is that you draw some surface, you give me the area of the surface you drawn, and you give me the electric field. And I can tell you how many charges are inside. Or you tell me the charges inside, and you tell me the area, and I'll tell you the electric field, or vice versa. And so this is helpful in some cases, and we'll go through it in a bit. Now, to add one more thing to this example, some questions that you'll get is, what if I have a plane, right? So I have a plane that's looking like this, and I have some electric flux or flux coming through here. So actually, maybe I drew that a little bit, so I'll make it even smaller. Okay, and so what if there's electric flux coming from the bottom at an angle like this? Remember how we said, so if I put a proton, let's say right here, and this proton, throws away electric fields, and there's some flux going through here. Right? It's the same thing as if when I had it earlier, when it was like this. The flux that we were counting is the ones that were coming straight out. And so you see, this is not coming straight out. This angle, there's some flux going this way, well, some electric field, and there's electric fields going up. So this would be my x, and this would be my y. So which electric flux is actually the one going through? Well, the x is not going through. The x is just going on the plane. So if we were to look at this paper or plane from a side view, what happened? Dang. This is why this sucks. Okay, so the electric field is coming through like this and coming out from here, right? And what if I had the electric field coming here? Is there any electric field going through this paper? Well, no. Well, this is technically going through, going in from here and coming out from here. But we're more talking about the surface area, this area specifically, right? And so if we want to account for only the electric flux that's actually going through here, we got to split these arrows in x's and y's and only account for the y, right? And so how would I do that? Well, if I have this as my area vector, that's where my area is pointing towards, then this electric field line that is going out, right? Going out all the way, then I obviously want only the sign of it, right? But I'm not gonna go ahead and find E, then find this angle, when I can just find my A vector and find this angle instead, and then cos it. Remember, sine gives me the opposite, and cos gives me the adjacent. And the electric flux that's here, so I just gotta do is split this whole triangle the other way. So my x will go this way, and my y will go up from here. And that's my angle. And so that's why what we usually say is that the electric flux is equals to the electric field times the area, but we only want the flux that's going through the area. So then we cos it, and we give it theta. And that will only give us this electric flux that's going through the area, out from here, and not the ones going across the area. And so if I put a circle here, and imagine this is a shaded circle, and I put, an electron here, let's say, a proton, and the flux goes through. You see, the face of my object, or the area I want, is also facing in the same angle. So what's the angle here between the E and the A? It's 0. If I look at it from the side, and I flip it upside down, the electric flux is going up this way, and the area is also facing the same direction. So the angle here, well, there's 0. So cos of 0 is 1. And that will give you the maximum flux. But if I tilt this, and I still have my electric flux going up this way, well, how much of it is actually going in, and how much of it is just the, the sideways? And so here, if my area face is pointing that way because I've, tilted it, then this electric field is up here. And the only one that's going into the page is, well, the cos, the E cos theta. That's the only one that's actually going through the paper, or the page, or the mirror, or the glass, whatever it is. So I hope that kind of explains it. All right. So what I'm trying to say is, for this type of problem, you see how it's coming out like that? Now imagine this was only a sheet on top. The electric flux will be going through it. But if I tilted it, then not all the electric flux is going through, because it's going through at an angle. Okay? So I hope that really explains what's going on here. And that is electric flux, and that introduces two things, which is one, I, this is to sum it up, this is flux, equals to E, which is the electric field, times the area. So this is going to be area of, you can say plane, or area of anything really, or area of a circle. Okay, and this is, we're going to do cos theta. Theta is the angle between electric field and the face where you're trying to measure it from. So if this was my box, obviously this would be the face, which is coming out of the screen or into the screen, right? Now if this box was, I'm looking at it from the side, it would look something like this. And so let's say the area I'm looking for is this. And so that my flux is whatever is going through here. If flux was going at an angle, then my E is this theta, right? And so if I do E times cos theta, that'll give me only the E in this direction. And that's what I actually care about. Whatever is going to in the same direction as your area that you're counting for. Okay, so I hope that really takes it over the top right there. This is a very important concept. We will be using it a lot. That's why I'm trying to repeat myself many times. And our second equation is, we know it's the integral of our A times our dA equals my charge N over epsilon naught. This one is the actual Gauss's law formula. This one is a flux formula, which is, I don't know if Gauss made that one, but I know this one is definitely the one, because this dA is for this dA, after you integrate, your E is constant usually, almost always. Like we're not gonna do a non-constant electric field in this course. It's gonna get way too complicated. And so my dA is actually, after I integrate, is just A, right? So that equals my Qn over epsilon naught. This A is your Gaussian. I think it's called Gaussian, like this. Area. What is Gaussian area? Remember how I said, if I give you some electron and I make a circle around it, and can you tell me how much flux is here? Then, well, yes. And if I also give you the electric field, and I give you the area, you can tell me how much charge is in. Because how many lines is totally correlated with how much charge is inside. And so that is my Qn, is what charge is inside. This is the electric field emitted by the charge inside. This is the area around the charge inside. Okay? And so this area can be literally anything. Because remember how I said the flux will always be the same amount. Doesn't matter where I draw my surface. I hope that really prints it in your skulls. Alright, and as always, I will never leave you guys without doing a bunch of problems to prove that what we did is right. And so here is the electric field, or Gauss's law homework for the unit. And so starting fried, but besides that, question number 1. The electric field is constant over each face of the cube. So we have this cube. Let's steal that. Oh, mine now. This is my diagram now. Boom. Alright. So it says that the cube shown in this, does the box contain positive charge, negative charge, or no charge? Now obviously the answer is front of y'all faces, but don't look there. Now why is it that way? So if I have a box and I have some electric field going towards, that means there's some charge negative. And if I have some field being emitted outside, then that means there's also some charge positive. Now, if I take the sum of all these, there must be some, it's either positive, negative, or they equal out. How do I find that? You just gotta add them together, really. It's not that hard. And now, why is this possible? Is remember how we said electric field is proportional to how many lines there are? Oops. And also the electric field is proportional to the charge. So the more the charge, the more the electric field, and the more the electric field, the more lines we get. And so if the strength of the electric fields are 10, so we have, this is one thing coming out. So let's actually make an out column and an in column. My out is 10, that's done. I have another 10 here out, okay, that's done. I have another 20 out, that's done. Now this total is 40, we have 40 lines out. And now, well, if I have 10 in, and I have another 15 in, and I have another 5 in, this equals to 25, 30. And so we know there's more lines out than lines in. So if we sum all the charges inside this random ass cube, we'll find out it's more positive than it is negative, because there were more electric field lines going out than there were going in. And that's your answer. That's why it's positive. All right, now for problem number 2, let's draw our diagram. Oh, actually, I was about to say let's draw our diagram, but I forgot I was Arab and I can just steal this. Whoop, mine now. All right, so now when I'm looking at this electric flux, and so what is it saying? The electric flux through the surface shown in the figure is 25. So my electric flux caused by this electric is 25 newtons per meter squared per coulomb. And what this means is, well, yo bro, there's fucking 25 lines coming out of this page. Actually, is there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Nowhere close. But the way you can think about it is when it says this eye, this ugly looking eye, you can think, well, there's 25 little lines coming out of this. All right? And these 25 little lines, it's asking you, what is the electric field strength? So it's asking you, what's my E? All right? And remember how we said, well, my strength is actually definitely correlated to how many lines there are. The stronger my electric field is, the more lines there are to, well, explain this electric field. Now, why is that? Is because each electric field line has a constant value. It's actually pretty funny. But each electric field line can only be so much. So as you increase your electric field, there will be more lines to represent how strong you are. So it's like you can only pull so hard with the rope, and if you want to get stronger rope, like pull stronger, then you need to get more ropes to pull from. And that's the same thing. And so my equation will tell me, I'll tell you how many lines you need. So that's my EI. If you tell me what strength you want and how much area you want to cover. And obviously, if I take this line and I pull at an angle like this, then the force I'm exerting on the E to the X, well, is not really doing anything. I'm pulling sideways. That doesn't really do much. But the force that I'm pulling on my EY, well, that force matters because that's the one I'm actually trying to pull on. And so that's why we only consider my EY, and that's why there's a cos theta. Now what this cos theta represents is you can either do sine of this angle, but this angle obviously is this EY, and that's your angle 60. But if you're using this angle, you'll have to do cos to give you, I'll do this so you can see it, so you can get this EY. All right, as you can see, this pink line, this is your actual natural E, and you split it into two vectors, and the one in the X, like we said, is useless because it's pushing sideways. But my E and the Y is what matters. And so, well, let's plug things in here. We have 25 equals E I don't have. My A, well, we got our area, which is 0.1 times 0.2. Now I converted these to meters because your flux is meters squared, so you can't keep these in centimeters. And my cosine, well, like I said, if we use cosine, we're using this angle because, well, EY. So if I look at this triangle, this is what it actually looks like. This is my E, this is my EY, and that's my angle. Well, we know sine will give me the opposite, and I know cosine will give me the adjacent. So cosine theta is EY over the hypotenuse, which is E. Taking E to the other side, E cos theta will give me that EY. But that's only of this angle. The angle they gave me is the bottom angle. So I can either do 90, so I can either do, well, this is what it looks like right now. So I can either do 90 minus the 60 they gave me, which is 30, and I cosine, or I can just use the 60 they originally gave me, and I do sine, because this is also EY on the opposite side. And so here I can either use 30 or sine 60, and that's the same thing. And so now isolating, you'll get 25 divided by 0.1 times 0.2 cos 30. Plugging this in. 25 divided by 0.1 times 0.2 cos 30. That gave me 1443, or 1.4 times 10 to the 3. And that is our answer right here. Okay. All right, hello people. This is problem number 3. And this states is we have a 2 centimeter by 3 centimeter rectangle lies in the XZ plane. Let me go grab some, or steal some, I should say. Voila. There you go. We stole a little thing. Okay. So what this states is that we have a 2 centimeter by 3 centimeter rectangle lies in the XY. So this is my X and that's my Y. So it lies something like this. That's my plane. That's my plane. All right. So what is the magnitude of the electric flux going through the rectangle if we have an electric field equals 100 in the ith direction? And remember we said I represents X, J represents Y, and K represents Z, minus 200 K hat newtons per coulombs. And so this is the electric field we have that's been emitted, and we have a plane that is in the XZ. So if we take this and we actually find where the angle is, we know that this is going to the right because this is positive, so it's to the X. Well, actually, let's draw it along this X, so it would go in the X, right? So that's my first E in the X, and 200, negative 200 in the K, so it actually goes down in the K. And that is my E in the K, and that represents my Z. So I should probably put Z instead. All right. Now that means my electric field goes from this point to that point. I can actually move this out of the way, move this X out of the way. This is going to be my EX. And so that means my E vector goes across that way, from here to here. And so if I'm actually looking at it from the side, what I'll see is this is my little plane, right? And the vector is going from down here all the way up here in that direction. That's me looking at it from this point of view, from the front. Okay, so I hope you could see it. Now this electric flux, as we see, oops, I actually drew this wrong right here. Apologies. But this electric flux goes from the X downwards. Ooh. Actually, I think I made them both wrong. That's funny. I hope you guys see through my mistakes and learn from them. Because it's supposed to be, you know, what is it called? Face to tail, head to tail? Face to tail. But, yeah, so if my X was going this way, right, and my other one is going downwards, this is my EZ, that's my EX, this is the arrow, it's going this way. And lol, messed it up. Oops. That's my E. Okay. So it's coming down this way. But it's not going through it. Right? It's not going through it. It's just coming down that way. And so the electric flux here is actually 0. Because, well, remember how we said if I have a plane, then the electric flux is only the one that goes through it, not the one that goes past it. And so if my plane is this way, then my area vector is straight this way. That's my area vector, right? But the flux is going down from the side, and so nothing is going through. So there's no flux. All right, so now clearing this image, I hope that really explains it. If you guys understand, it's like speed through. Don't watch something you understand, unless you want to really concrete your belief. My next question says, well, what if I have then 100 in the x? So what if I have 100? Actually, I'll just draw it on the board. If I have, here, I should draw it here. So if I have a flux that is going 100 this way, and it is going negative 200 in the j. And the j is obviously my y, so now it's going along that way. It's not going down or up, right? And so my electric field now is this way. And so now I know, right, if this was my plane, right? Ooh. If this was my plane, and then my flux, I'm going to change the color of this so you can see it easier. My flux is now coming from here and out from here. How do I know this? Because they said there's 100 EX, and they said there's, well, from tail, they said there is also EY that is negative. So positive in the X and negative in the Y. That makes some flux coming like this. And so if I'm looking at it from the top, what I'll be seeing is this is my plane from the top, and my flux is coming like this. Right? And so this is actually going through. And so my area vector is this vector. That is my area vector, and it's on the y. It's on the y-axis. So this is my y-axis. This is my, obviously, x-axis. And my z comes out of the page, right? And so looking at it from the top, my flux is now going this way and out that way. And that is my E. Now, well, what is my E? They did tell me that my E in the x is 100. So the flux that's going this way is 100. And the flux in the y, in the j, they said it's negative. Negative 200, I believe. Actually, I'll give some more space down here. EY, that's too many arrows. EY is 200, negative. And so now I can calculate the flux. And so the flux equals, that's too small. The flux equals my electric field times my area cos theta. But obviously, my electric field is going in the direction of my cos, of my area. So my cos is actually, well, my angle is 0. And cos of 0 is just 1. Right? And so this equals 200 because I'm only looking at my y times the area. And the area, does it give? 0.2 times, well, 0.02 times 0.03. And that equals 200 of 0.02 times 0.03. Negative 0.12 flux. Newtons meter squared per coulombs. And that is 0.12. We don't make mistakes. All right, now we're doing problem number 4. And again, like always, Arabs do what Arabs do, which is steal shit. I'm gonna take that. Well, actually, we bomb stuff, but same thing. Okay, so in this question, it says 3 Gaussian surfaces and the electric flux through each. What are the 3 charges? So there's a Gaussian surface. These are Gaussian surfaces, imaginary things they made in your head. And it's saying, well, each one will tell you how much flux there is. So if I take this hole, so if I split it, and I'm gonna use a different color so you know exactly which one I'm talking about. If I take just this one, actually I'm gonna make this even thicker. So if I am taking only this surface right here, oh, this actually will fix it. Let's go. If I take only this, right, and I grab it and I'm gonna take it outside here. Okay, so here, let's actually even draw these. Right, and so if I take this whole diagram that I just made, and I take it outside here on the side, you can see that, well, it tells you the electric flux inside here is a negative Q over E naught. But this is just the epsilon, so who cares about that? But we know there's a negative Q here. And if I do the same thing to this section now, right, and I have my Q2, and I have my Q3, and I steal that too, then as we can see, my Q1 and Q2, or Q2 and 3, has negative 2 Q's inside. Okay, now if I do the same thing for my, obviously, one last time, sorry. You're probably like, oh, we just do it already. Why are you just, if I, oh my god. Okay, let's just grab it. Just sometimes I know y'all get bored, so I have to keep saying shit. Alright, so now back to this. This is 3Q. Now, how can I find each one? Well, if I give this, let's say 1Q, and I give this 2Q, then this would be a total of 3Q, so that doesn't work. If I give this, let's say 2Q, or actually if I give this 1Q, and I give this negative 2Q, then, well, when I add these up, I'll get a negative Q, which is okay, so following so far. But if my Q3 is negative 2, then this has to be 0 for me to get negative 2. But it's not, because there's obviously an electron, so there has to be some charge. So, well, then, okay. What if I flip these then? I'll put this as Q, and I'll put this as negative 2Q. And I can, well, now name this as negative 2Q. Then name this as 1Q, and make this negative 3. But now if I make this negative 3, you see, well, that doesn't add up to 5. I have 3. That doesn't add up to 3. I have 5, negative 5. So basically you want to keep playing with this until you get something that satisfies all the conditions. And so let's see what we can do them here. So there's another way you could look at it. You could say, well, let's use the same, actually, let's use some bright color here. Whatever. Okay, so you can see if these two holes share, or these two surfaces share, right? Okay, well, this gives you a hint, because this one is negative, and this one is negative. But this Gaussian is positive. So this has to be negative of something. So, well, if this causes negative 1, and this causes negative 2, then this must be, let's say, negative 3. Well, in that case, then this has to be 2, and this has to be 1. So now, when we add these two together, I will get a positive 3. When I add these two together, I'll get a negative 2. And when I add these two together, I'll get a negative 1. And that's one combination you can make it. I wonder if that matches their combination. Q1 is 2, which is what we had. Q2 is just Q. Oh, actually, that's the same. Oh, I didn't pay attention. Lol. So I hope that kind of explains it. All right, so question number 5. They give us this little diagram that we, of course, stole and they ask us what's the electric flux, total electric flux that is coming out of the cylinder. And when they talk about coming out of, they specifically talk about this little circle right here. All right, that's what they're talking about. What flux is coming out of there? The first thing we're going to start with is, well, my electric flux that this red one is creating, which is going through, or electric field, which is technically, electric flux is how many electric field lines there are. So if there's a lot of electric fields, there's a lot of electric fluxes. All right, so now my negative is also pulling electric flux out, right? Because the electric field line goes towards the negative. And so whatever is going in from here is going out. So if I give you an electron here, and I give you a box here, and I give you a proton on that side, and I give you an electron on this side, then remember when we did this example, we said we added everything in, everything out, and we saw what charge it was. Now, if they're both the same amount, oops, let's do that like this. If they're both the same amount, then whatever's going in is coming out. And so inside here, the electric flux is just, there's zero. Whatever's going in, going out. And so that's a no bueno, as Brianna would say. But the electron inside is, well, that one is emitting outside. And it's from inside out. So whatever's going in is not going out. So when you add all the sums, these ones don't really matter for shit. But the one inside actually does matter, because these just cancel each other out. But the one inside doesn't. And so this will create some electric field that's going that way. And that is the flux coming out of this cylinder. And so my equation for electric flux equals the electric field at this point, right, times the area times cos theta. So if I'm looking at the cylinder from the side, there you go, and I have a proton inside, then the flux going outside is out of here, right? So this is my flux, and it's in the same direction as my area that I'm looking for, which is a circle. Therefore, what I can say is my cos angle, right? Usually if you have your flux going that way or your electric field going that way, then your flux is only your EY, but my electric field is that way. Therefore, the angle between, so usually this is the angle, but now the angle is, well, 0. There's no angle. And so 0 of cos is 1, and so cos goes away. Now, the electric flux of my EA, well, what's our area? This is a circle. Area of a circle is pi r squared, right? Now, what is my electric field at this point? Now, there's obviously two ways we can check for that. One is using Coulomb's law, which states the electric field at some point equals to K Q over R squared. The other way we can say is also Gauss's law, is my E dA equals my Qn all over my E naught, right? Now rearranging this, my E is a constant, comes outside. The integral of my dA is just A, and that's Qn over E naught. And rearranging again, what I'll get is Qn over E naught, my area. Now substituting my area in, what I'll get is Qn E naught 2 pi r squared. And while you can actually see the similarities here, and that between this and this, remember your K is 1 over 4 pi epsilon naught, right? And so you could use either or, and you'll get the same result. I'm going to use Gauss's law here. And so when I plug it in, what I'll get is 1 over, wait, what did I do? 1. It's Qn over my E naught 2 pi r squared times my area, right? That's not gone yet, which is pi r squared. Wait, where did I get the 2 here? Oh, there's no 2 here. Just power squared. Yeah, I don't know where I got my 2. Interesting. All right. And so what will happen here is these will cancel out. And what we'll get is the charge in over the epsilon, or permittivity of free space, equals my flux. So if I do this, I'll get 1 times 10 to the negative 9 all over 80.85 times 10 to the negative 12. And when I do this, what I get is 112.99, which is the same thing as saying 0.11 times 10 to the negative, to the 3, right? Because 1, 2, 3. Newtons meters squared per coulomb. Or I can also say, which their answer was 0.11 kilos per newtons meters squared per coulomb. All right? That's just units and conversions, nothing really too special. Hello guys, now, oh, I forgot to steal the picture. Wait, no, not this picture. Oh, there's no picture to steal. Okay, never mind. Well, we're doing question 6 here. And we have 10 nanocoulombs charge in a cube. So let's draw this cube. Ooh. There you go. And it's saying inside this goddamn cube, there's a 10 charge. So positive, and the charge on this is 10 times 10 to the negative 9. And saying, what is the electric flux through the top surface of the cube? Only the top surface of this cube. Okay? And so if this was creating an electric flux upward, or well, actually, let's check the electric flux all around it. How much does it create in total? Well, we know IE, electric flux, equals E times A. And so, well, I give the electric field, which in this case, we know my Gaussian, what Gauss's law says, is that the electric field given at a certain point, so E dA equals Qn over E naught, which is just EA, equals Qn over E naught. And so what this says is that if you give me this information, then if you give me the electric field at some point area, then I'll tell you what the charge is. And so that's Qn. I just subbed it in, subbed the whole thing in. This equals this. What this equation says is if you give me a charge, okay, so what this equation says is if you give me a charge, I'll tell you exactly how many flux lines it creates. Okay? This will tell me exactly how many flux lines. Remember in the video, in the lecture, where as I increase the magnitude, more lines appeared? This equation will tell me how many lines appear. And that would be my flux, right? And so now plugging things in, I'll get 10 times 10 to the negative 9 all over 8.85 times 10 to the negative 12. And what this will give me is, where is it? You know what, I'll just put in. I thought I had the answer somewhere, but I didn't. Well, it is what it is. Alright, so the answer I got was 1129.94. So it's safe to say that this creates 1130 flux lines out of everywhere. So this way, this way, this way. When you add them all up, there's 1,130 of them. And so what I want is only through the top face. Well, if I have 6 faces here, right? These 6 faces. So if I divide this by 6 faces, I'll know how many flux lines go through each face. And so that would be divided by 60, oh, not 60, 6. That will be 188.3. Now taking this 1, 2, 3, I'll get 0.19. So 0.19 flux lines, kilo flux lines, per newtons per meter squared per coulomb. And so this will tell me there's 188 flux lines going through the top surface. And that's the same thing they got here. All right, so for this question, I stole a ball, and that is question number 7. So for the question number, it's not exactly this. I'm just using this as an example. So it says a neutral conductor contains a hollow cavity. This is my neutral conductor, and it's metal. That's why it's a conductor. And it contains a hollow cavity, which is this part, right? And in which there is a 100 nanocoulomb point charge. So we're going to ignore that for now. In this example, as you can see, when I put a positive, don't think about it in a way where there's now the positives move to the left because they repel, and the negatives move to the right because they got attracted. Well, actually what happens is, here, there were these negatives were actually here, and this was neutral. But when I put a Q here, all the negatives went on the side, and they left their positives. Positives don't move, remember that. Remember how it was, I believe, 1.67 times 10 to the negative 27 kilograms, that's a proton. And this is an electron, or vice versa. Actually, no, it can't be vice versa. But you see, my proton is a lot heavier than my electron. So my electrons move usually around in a conductor, okay? And so that's why all the negatives come to the right. The positives don't go to the left. It's just, well, the negatives left them. So now there's a lot of positives here with no negatives. So we say, well, on the left side now it's all positives. On the right side is negative. Your electric field inside will always be 0. Now why is that? Is because when I have a positive here, and a negative, and a positive, and a negative, now what happens is these will push off each other and make sure they're all evened out so that they're not pushing each other. If the electric field was not 0, that means there's some force inside, which means the electrons are moving around. But after you leave it for a while and they stabilize, the excess goes on the outside, and the inside will always have E0. Alright? But what happens if I, well, put a positive here? So let's get rid of this now. Imagine this is not here. So let's get me a little white one and remove this stuff. So imagine this is not here no more. These are not here no more. So this is neutral, assuming I don't even have this. So this is now neutral ball, right? Now when I take this and I put inside a electron, that is a proton that is positive, with 100 nanocoulombs of charge, then what happens is all the negatives will come on here because they want what's inside as E equals 0. So first, this proton will slowly start attracting electrons, and electrons will slowly start moving, and they all gather up here, right? Leaving all the positives on the edges outside, right? Oops, like yeah. So within the surface, and when we like to put them, we actually don't like to put them up here, we like to put them on the outside. The reason being is so we can be sure that on the inside, the electric field is 0. So this stays like on the outskirts, the very outskirts. Okay? And so what this is saying, now what it's saying is a charged rod then transfers negative 50 to the conductor. So this is what it looks like. Now we have a E0 outside, inside, but if this was 100, then 100 of these got deprived outside. So on the outside, I have now plus 100, right? The other way you can look at it is if I take this whole thing and I add 100, if it's neutral, so right here it says neutral, and if I add 100 nanocoulombs to it, then the total charge will change to 100 nanocoulombs. And so now it was neutral, and now it has 100, with this 100 on the outside, you can think. Now if a charged rod of negative 50 gets tapped, then all this negative 50 will transfer over and connect with these, right? But well, now it's not 100, it's just plus 50. Afterward, what is the charge on the inner wall of the cavity and on the exterior surface of the conductor? Well, on the inner side of the cavity, So you see, this is the cavity, and it's asking what is the charge on the inner wall of the cavity. So it will be negative, right? So it will be negative 100. All these are on the cavity side. And what is the on the exterior surface of the conductor? Well, plus 50. That's your answer. All right, now for this type of problem, we have find the electric field inside and outside a hollow plastic ball. So actually, same exact problem. Where's my picture? There's my picture. Let's delete all this weird things. Oh no. Nice. All right. Now, obviously, we're going to ignore all the positives and negatives here. We just want the ball. And it's saying find the electric field inside and outside a hollow plastic ball. A hollow, I think it's called. Plastic ball of radius r. So we know, actually, let's get a hollow ball. Let's steal one. Okay, sorry, but this is the best thing I could steal. Okay, so find the electric field inside and outside a hollow plastic ball. So this is plastic. This is an insulator. Insulator. And what we're saying is the electric field inside and outside a hollow plastic ball of radius r. So the radius here is capital R. That has the charge Q uniformly distributed on its outer surface. So it has uniformly distributed. I'm going to actually use colors here to make it look pretty. On the outer surface and so on. Watch this. I'm going to do the smartest thing. Big brain stuff. Watch this. I mean, this is not big. Oh, shit. No. That's not what I meant. There you go. Big brain. Boom. Big brain. Okay. So, the point is, as charge Q uniformly distributed on its outer surface. So we're looking for the electric field inside and outside. So, okay, what can we do here? Okay, so the electric field here. So if I go right here, remember how we said for an insulator, since oh my god, you know what? Just give me the dance circle. There you go. And remember how we said since the insulator stuff can't really move inside, even though it's hollow. By the way, for this part, imagine it's whoops. For this part, imagine it just goes like this, continues, like there's no hole here. And so what's the inside is always E0. And that will always be the case, especially even for an insulator, because things can't really move. Now it's this telling us there's some charge outside. So how do we find this charge? If I make a Gaussian surface, right? Oh my gosh. Jeez. Okay, you know what? Give me the goddamn circle. Alright. Now if I make a Gaussian surface on the outside here, to include all these little things. And there you go. Then I know what my Gaussian surface, and by the way, imagine this is, the electrons are so small, this is going to be basically the same as this circle, right? Like, it's just, don't think it's this difference. But what we're going to say is, well then, I know my Gaussian surface is E times A equals the charge in inside this surface all over epsilon naught. So rearranging this, what I'll get is, well, E goes on the outside, absolute, and this is dA. dA just becomes A equals Qn over E naught. And now, what is my area of a sphere equation? Is 4 pi r squared. So E, well, first let me rearrange. That's Qn, E naught, and this is A. And so my Qn, I'll just denote as Q, because they're saying up here, where is it? They're saying has charge Q uniformly distributed on its outer surface. So the charge inside here is just that Q they're talking about. And so this is just their big Q all over. Now my E naught, my sphere is just 4 pi r squared, and r is this big R, right? like I said, this Gaussian surface is basically right on the surface. And because these protons are so small, right? And so that equals my electric field. And so looking at the equation they have, 1 over 4 pi epsilon naught. So we have 4 pi epsilon naught. And you have r squared q in the r direction. Right? And that's this question. All right, now we're getting to a little bit harder questions. And here we have a long, thin, straight wire. So long. And when they say thin, they mean a linear. Right? So this is like 1D. And this is, so what are we saying? A long, also long. This is infinitely long. All right. Straight and linear charge density lambda. So it has some charge density lambda. Runs down the center of a thin hollow metal cylinder of radius r. Okay, so I did not see that one coming. Okay, so it runs through the center of a thin hollow metal cylinder. So there you go. And this actually, that looks horrible, but what I was trying to make this look like is more of a cylinder, right? And that is the cylinder here. So if I copy this and bring it here, that is what it looks like. Okay. And the cylinder, is the cylinder also infinitely or no? The cylinder has a net linear charge density. So this is 1 for wire or whatever this rod is, and 2 is for this. All right. Now it has hollow metal cylinder of radius r. So this has some radius r, right? And the cylinder has a net linear charge density. So we got the linear charge density of 2 lambda. So, okay, 2 lambda 1. Assume lambda is positive. So assuming this has a positive charge, right? And this also has a positive charge because it's 2 lambda. Inside, find an expression. So the cylinder has a net linear charge density lambda. Assume lambda is positive. Find expressions for the electric field inside the cylinder when r is less than big R. So what this is saying is it's saying looking from the top, right? I have this cylinder and I have this little also rod. And this rod is 1D, so it's actually just a dot. You can think about it, right? Both of these things are 1D, but I'll give them a little 2D shape just for fuck's sakes. All right, so let's make this a little more realistic. That's what they're talking about. All right. So what they're saying is check the electric field. So I'm going to use a orange for electric field. I'm looking for the electric field within this orange circle. And obviously this orange circle is almost the same. How do I know this? I'll show you in a bit. Let me just, okay. So we're saying it's when R is the distance from this wire, all the way to the outside. They're saying, and big R, that is big R. And this is little r. They're saying when little r is less than big R. And so that's, you see the circle is less than the big circle, right? And so the question is saying, find an expression, right here, find an expression for the electric field inside this. And so we're looking for the electric field inside this orange. And so I'm going to do it in orange as well. Now I know the Gauss's law, so I'm going to assume this orange is, I'm going to make it a Gauss's law. Or not Gauss's law, Gauss's surface equals E on the outside, EA, equals my Q inside, all over my epsilon naught. Now redoing this, my integral, I'll get EA over Q naught or Qn over epsilon naught. Now, since we know that the charge density of this wire equals lambda, right? We know lambda equals Qn over some length L. Therefore, we can rearrange this to say my L of this rod times lambda equals my Qn. And replace that in. So EA equals L lambda 1 all over E naught. Now obviously I'm looking for the electric field. So what I can say is the electric field equals L lambda 1 over E naught. Now what is the area? Obviously I am looking for the electric field that is coming out from here, from the cylinder. Let me see what they're looking for. There it is. Find the expressions for the electric field strength inside the cylinder. So it's just the electric field anywhere inside here. So from this point to this point, from this point to this point, from this point to this point, just the electric field at any given point. So the electric field at any given point is, well, this equation times A, which is the area of a cylinder, and that is 2 pi r. Area is 2 pi r, so L lambda 1 equals epsilon naught 2 pi r times L. L is the length of the cylinder. That is just the equation for area of a cylinder. And so the L's cancel out, and what we get is E equals just lambda over epsilon naught 2 pi r. And if I give any r, so I give it obviously lambda, and if I give it any r, anywhere in here, whether it's here, it'll tell me the electric field there. Okay? And so now what is part B? Did they also get the same thing? Yeah. Lambda 2 pi epsilon naught r is on here. Alright, now part B. Outside the cylinder, in what direction does the electric field point in each of the cases? Alright, well, we know on the inside, since this is positive, the electric field will point outwards. So that's that. Now, redoing this case on the outside, right, so for this section, what we're going to get is obviously my circle, or my cylinder, and I have a little eye inside here, well, rod, sorry, and on the outside is where they want me to calculate the electric field. All right, now obviously I know that on here this rod is positively charged. That means all across here is negative because of this positive, and on the other side is all positives. But that doesn't really matter in our equation here. Because our equation, what it says is, well, this is my Gauss's surface. So Gauss's surface equals E times dA over my U inside all over my epsilon naught. Now we know that this surface is 2 lambda, right? And we know that this is 1 lambda. And so if we were to rewrite this, well, first let's rewrite this. This is E A equals Qn over epsilon naught, meaning EA equals Qn over epsilon naught A, right? Now what is my area of a cylinder? My area of a cylinder, so I have still Qn. Area of a cylinder is 2 pi r, and I have L. And so what is my Qn? Qn is obviously whatever the Q here plus whatever the Q here. And so lambda equals Q1. This is of the rod. Let's say Q rod over L. And I have another one that's 2 lambda, which equals the Q of the cylinder, Q cylinder over L. I mean, what if I divide it by 2? If I take this lambda and I divide it by 2, oh sorry, if I take this lambda and divide it by 2, then I'll get lambda equals Qn, well, Q cylinder, all over L times 2. And you notice now this lambda equals this lambda. And so, well, if I do it, then I'm just trying to prove something here. You don't got to do none of this. But in case you don't see it, the length is the same for both. Over 2L. And if I take 2L to the other side, I'll get 2L over L. And this we have Q rod. This equals my Q cylinder. And this will cancel out, making this 2Q of rod equals Q cylinder. Right? Now if I re-isolate, then Q rod equals Q cylinder divided by 2. And that's what I have up here. Right? And so what I can say is, well, then I have now 3 lambdas, which equal some total Q all over some length L. That's what I was trying to prove here. Right? And so my Q's in total is I have this Q, which is the Q of the rod, plus 2 of the Q's here, of the same rod Q, right? And so what I get is, well, 3 Q's. And now what is my Q in other words? Well, we know it's 3 lambda times L, right? So if I have lambda equals 3 Q's over L, then I can rearrange. And I got, well, sorry, this would be Q's over 3L. And if I have 3 lambdas, this will be L equals my Q inside. And so take that, put it in here. I hope this is clarifying and not too complicated. I know there was a lot of nonsense here, but I know some people don't see it. If you see it, that's good for you. You see this cancels out with this, and what I get is 3 lambda over epsilon naught 2 pi r. And what did they get? 3 lambda 2 pi epsilon naught r. Nice. That question is done. And this is our last unit, or last question of this unit. And we would have covered 4 units now. And we have, what is this? Let me count. Shit, what's 10 minus 4? That's 6 plus 2. We have 8 more units to cover. Some of them will fly through, like AC resistors. These are the easy units. But for, I'm not even sure what's after this one, so we'll see. Anyways, for this question, it says the electric field must be 0 inside a conductor in electrostatic equilibrium, but not inside an insulator. It turns out that we can still apply Gauss's law to a Gaussian surface that is entirely within an insulator by replacing the right-hand side of the Gauss's law. So we know Gauss's law right? And it's saying you replace that right-hand side with Qn over E, which is supposed to be the permittivity of the material. Still the same, except my permittivity now is for that specific material. And so it says suppose that we have a 50 nanocoulomb. So we have some type of ball, a shell, and we have a positive Q equals 50 times 10 to the 9 coulombs, right? Point charge is surrounded by a thin 32 centimeter diameter spherical rubber. So this rubber is thick, and we have some distance d here, right? This distance d is 0.32 meters. Oh, it's thin actually. My bad, I made a mistake here. And so it's thin, but it says the diameter of the spherical rubber is 32 centimeters. So the distance here, I don't think this is supposed to be thin, by the way. This area here is very thin, so don't think that it's anything. Okay, we'll give this D, and D equals 0.32 meters. Okay. So 32 diameter spherical rubber shell, and then the electrical field strength inside the rubber shell. So my E here is equals to 25. So my E here is equals to 2.500, not 200 like this, for coulombs. What is the permittivity of the rubber? And so what I'm assuming is, since this is the electric field strength inside the rubber shell, I'll assume that is the electric field inside here. So if I take Gauss's law, I take this whole thing on the inside here, and actually I'll use a different color for it. I use this as my Gaussian surface, right? Oops, that's not what I meant, man. There you go. So if I take this as a Gaussian surface, then what my result is, well, the equation's still the same. And this would be my Qn over my E. And now integrating this side, I'll get EA over Qn E. And now taking Q to the other side, well, actually I'm supposed to flip it. I don't know why I did that. So here would be epsilon, and this would be my Qn divided by my electric field times my area. Now, what is my area of a sphere? It is 4 pi r squared. So here would be the charge within this circle, and my E here is, well, actually I'll write it later. My area is 4 pi r squared. My r being my D, well, half my D, right? And so applying everything here, what I'll get is E equals my charge, which is 50, all over my E, which is 2500 times 4 times pi, all times D, which is 0.32 divided by 2, all squared. And let's see what we got the permittivity to be. Almost there, almost there. 0.32 divided by 2 all over squared. Alright, and I got 6.2169 times 10 to the negative 11. And that's also what they got. And that's dubs. Thank you guys. This wraps up Gauss's law. And if you have any questions, please do comment.